I thought this 2011, that's actually HSC Extension 1 question, was worth looking at. It's actually worth a total of 5 marks, and while on the first read through it might seem a little bit complicated, I think as you start working through it, you'll see that really there's nothing terribly difficult about it, and would have been a nice, easy 5 marks. Okay, let's have a look. It says to test some forensic science students, an object has been left in a park. At 10 AM, the temperature of the object is measured to be 30 degrees. The temperature in the park is a constant 22. You know, by this stage we're thinking, yep, 22 is my constant, is my D. T0 is 30 degrees. The object is moved immediately to a room where the temperature is a constant 5 degrees. Oh, okay, so now we've got a different situation, and D is 5 degrees. 1. The temperature of the object in the room can be modelled by the equation. We'd expect this. This is of the format we're familiar. T is equal to 5 plus 25. Yes, that's the difference between the initial temperature, the temperature when the object was moved, e to the minus kt. And by the way, if I've only read through that once with you here on this video, of course you'll pause the video and reread that as many times as you need so that you can get a good understanding of what's going on. T is the temperature of the object, yeah, and T is the time in hours since the object was placed in the room, and K is a constant. So then it goes on, after 1 hour in the room, the temperature of the object is 20 degrees. Yeah, we're familiar with that. They give us a piece of information, pretty confident that we'll be using that piece of information to find the value of K. And it does say, show that K is equal to log 5 on 3. Okay, now I'm going to pause the video, write up the solution. Of course, I'm going to begin with the general form and work from there, and once I've filled out and got down to the value of K, then I will be back. Okay, I think I should just explain what I've got so far before I go through the entire solution. So here I've drawn a diagram. We're out in a park. It's a constant 22 degrees in the park, and there's an object which is 30 degrees. We've got some heat coming off this object. It's taken to inside a room, and inside the room it's only 5 degrees. So we've really got 2 situations. We've got the park situation and inside the room. In part 1, they ask you to focus on inside the room, and that will be illustrated. That will be the maths involved over here. Okay, but initially I started off, we know that it's a situation where the rate of change is proportional to the difference in temperatures. So we write dt is K times T minus D. Identify these things. T is a solution then to that differential equation is T is equal to D, the constant, plus A, which is just the difference at time is 0 between the temperature and the constant, times e to the minus kt. What we know in this situation here is that the object at time 0, and we'll see later, that actually that wasn't time naught, but for now, time naught is 30 degrees. The outside air is 22 degrees. That gives us an A of equal to 8. Not pursuing this situation any further because I know that the question asks more about what's going on inside the room. So we've got a second situation where the object is still cooling according to Newton's law of cooling, where the rate of cooling is proportional to the difference in the temperatures, and a solution to that is still the same solution, where T would be equal to room temperature plus the difference times E to the minus KT. So the temperature was 30 degrees. The constant temperature of the room inside is 5, and that then leads us to the calculation that A would be 25. Another piece of information we know is that when 1 hour later the object still measured 20 degrees. It seems to me this object's cooling quite slowly because it's in an environment of 5 degrees, which is pretty cold, and it's taken 1 hour for it to drop 10 degrees. That's pretty slow cooling, I would think, but let's see. Let's do some maths. Part 1 has actually asked us to, Part 1 has asked us to show that K is equal to, sorry about that, K is equal to the log of 5 on 3. And obviously the more of these you do, you'll become quite comfortable with the fact that this constant is a log of a fraction, and you'll be sort of expecting that. Okay, just move it up just so I've got a bit more space. Okay, let's get working on that. Oh no, hang on, I'll pause the video, write up the solution and come back and talk about it. Okay, so you can see that I've started with we're inside the room. T is equal to D plus A e to the minus KT, and inside the room the constant temperature is 5. The difference in temperatures is 25, and in order to find the value of K, we need to sub the temperature is 20 at time 1, and so we get this 20 equals 5 plus 25e to the minus K. Now subtract 5 is 15 on 25. Do we really want a fraction 15 on 25? That is 3 on 5. So 3 on 5 is e to the minus K, and we know that over here we've got to get the log of 5 on 3. We won't panic about that because there's some nice things you can do when you've got negative indices and logs. So for example, I'm going to take the log of both sides. The log of 3 on 5 would be the log of e to the minus K. Just working on this right hand side, I'm sure I could have done this more quickly by taking minus K to the front, but I was more fixated with the negative and wanting to ensure that I was able to swap there. So I just took the negative to the front, multiplied both sides by negative, which brought the negative over here. I could then put the negative in its power, and 3 on 5 to the negative 1 is, hang on, 5 on 3. Hang on, my mistake there. So raising 3 on 5 to the negative 1, turn it upside down, is equal to the log of e to k, bring the k to the front, log of e to base e is 1, so it's equal to k. So, I'm just going to leave this solution there and start a new
recording
video for part 2.